Welcome to VR 2026. Today, I'll present our work AdaEndoGS, Adaptive Enlightening Model for Endoscopy via 3D Gaussian Splatting. Our presentation covers 4 parts: research challenges and motivation, the AdaEndoGS framework details, our experimental datasets and results, and finally conclusions with future work. Let's start with the key challenges we address. Endoscopy is vital for medical diagnosis and minimally invasive surgery, yet it faces 3 critical issues. First, physical observation limitations of endoscopy, narrow spaces and fixed light sources lead to dark regions that hide key anatomical details. Second, 2D illumination enhancement methods lack 3D awareness, or leading to unrealistic artifacts and unstable brightness in rendering. Third, state-of-the-art 3D reconstruction methods like NERV and 3DGS only focus on scene recovery. They don't model or improve endoscopic lighting problems. Therefore, our work is driven by 3 core goals. First, bridge 3D reconstruction and adaptive illumination. Second, automatically detect dark regions and enhance them with physically consistent lighting without overexposing normal areas. Third, ultimately improve the clinical value of endoscopy by giving clinicians a clearer view of the surgical field. In short, dark regions in endoscopy compromise its utility. That's why we propose AdaEndoGS, a method that unifies 3DGS endoscopic reconstruction and physically consistent dark region enhancement. As you can see here, our method takes raw input, reconstructs the 3D scene, and lightens dark regions with clear visual improvements. AdaEndoGS is a 2-stage framework. Stage 1, 3DGS initial reconstruction. We extend standard 3DGS by adding surface attributes to each Gaussian, tailored for endoscopy's small field of view. This lets the model simulate light matter interactions, laying the groundwork for subsequent dark region detection. Stage 2, adaptive enlightenment. We use ray tracing to find dark regions, place a virtual light source at their geometric center, and apply PBR to ensure no overexposure in bright areas. The pipeline here shows the full process, with dedicated loss functions guiding each step. Next, we will introduce each step of our method in detail. Initial 3DGS reconstructions is to build an illuminatable 3D Gaussian model for endoscopy. We use EndoGS lamp to get accurate camera poses and point clouds, far more adaptive to endoscopy than traditional tools. We initialize the Gaussian model with the surface attributes I mentioned and optimize them with 3 key losses: normal consistency, image reconstruction, and edge-aware regularization. This ensures high-fidelity 3D reconstruction for the next stage. For dark region detection, we use a point-based ray tracing approach adapted for endoscopic tubular cavities based on the reconstructed 3D Gaussian scene. We emit multi-directional rays, calculate each Gaussian's transmittance as a visibility metric. Lower values mean darker regions. Then we use statistical thresholding to identify the major dark region, with the charts here validating the accuracy of our detection method. This step ensures we precisely target the areas that need enhancement. After that, we implement PBR-based adaptive illumination to brighten dark areas while preserving the original scene. First, we place a virtual light source at the dark region's 3D center with learnable intensity and attenuation for realistic light tissue interaction. Second, we decouple rendering into diffuse MLP for novel view generalization and a Cook-Torrance model for physical accuracy, matching human tissue material properties. Third, 5. Synergistic loss terms optimize lighting parameters with key focuses on color consistency for diagnosis, structural preservation of anatomy, and avoiding overexposure and artifacts. We evaluate AdaEndoGS on two complementary datasets, C3VD, which is a public colonoscopy dataset with detailed 3D ground truth, but it only supports qualitative evaluation. The other dataset is VEIDLA, our Unity 3D synthesized dataset with paired low and well-lit images and depth maps. It fills a critical gap in the field and enables both qualitative and quantitative evaluation of illumination enhancement. You can see the dataset generation interface here. We first test our 3D reconstruction performance against three SOTA endoscopic methods, 3DGS, EndoGSL, and Pre-Endo. By adding illumination-aware attributes and dedicated loss functions, our method achieves superior performance on both datasets. Qualitatively, our reconstruction has sharper geometric boundaries and more accurate texture versus baselines. The quantitative result is shown in the table. We outperform all competitors on key metrics for both datasets, proving a solid 3D foundation for illumination enhancement. Next, we evaluate our illumination enhancement against 5 SOTA methods, including 2D and 3D methods. Please watch the video. The video shows our method's superior continuity and stability. We recover clear anatomical details in dark regions with no color distortion, artifacts, or overexposure in bright areas. Quantitative results are detailed in our paper. In summary, our work has 3 key contributions. We propose AdaEndoGS, the unified framework for endoscopic 3D reconstruction and adaptive illumination enhancement. We achieve clinically valuable, physically consistent dark region enhancement by integrating 3DGS with PBR-based lighting optimization tailored for endoscopy. We construct the VEIDLA, filling a critical gap for quantitative evaluation of endoscopy illumination methods. For limitations existing in our method, our future goals are listed here. RGBD dependency. We currently need depth data. We want to extend to RGB only input. Single virtual light. Our current strategy works for major dark regions, and we'll develop multi-light strategies for scattered complex dark areas. Scene limitation. VEIDLA focuses on colonoscopy. We are trying to expand to laparoscopic scenes and add clinical expert evaluations. For more details, you can visit our lab website here. That's all for my presentation. Thanks for your attention.